You don't get a warning. That's the first thing you notice. There is no gradual transition. No gentle clue that tells you you've made a mistake. No moment where you can still turn back and say, all right, this isn't for me. The moment you arrive, the environment has already decided what will happen to you. And everything that follows is just the consequence unfolding. What's strange is that, at first glance, nothing looks dramatic in the way you might expect. There's no fire raining from the sky. No violent explosion. No cinematic catastrophe waiting to greet you. Instead, there is something far more unsettling, a heavy, unmoving stillness, a dense orange light that doesn't illuminate so much as suffocate, flattening everything into a uniform glow where distance loses meaning and shapes struggle to stand out against the background. You try to orient yourself, but the world doesn't give you enough contrast to do it easily. And already your instincts, your earth-trained expectations begin to fail. And then you feel it, not as a sharpudar, not as something sudden, but as a constant present, like a hand that was always there, and only now you've noticed it, pressing on you from every direction at once. This is where most people imagine something violent happening, but that's not how this works. The pressure doesn't attack you, it surrounds you. It persists. It removes your ability to resist over time. The atmosphere here is so thick, so massive, that it exerts roughly 90 times the pressure you experience on Earth, which means that simply existing at the surface is already an act your body is not built to sustain. There is no drama in it, and that's exactly why it's dangerous. It doesn't need to shock you. It just needs to continue. Now here's the part that usually tricks people, because if you ask someone what kills you on Venus, they'll say the heat, and they're not wrong. But they're also not thinking deeply enough. Heat by itself is just a number unless you understand what maintains it, why it doesn't go away, why the planet refuses to cool down even when it rotates away from the sun. The surface temperature sits at around 475 degrees Celsius. But the important thing is not how high that number is. It's that it is stable, locked in place by the atmosphere above you. There is no relief cycle, no cooling phase, no temporary escape. The system has no intention of giving energy back to space in any efficient way. So whatever heat arrives tends to stay, and once you begin to connect those pieces, you start to see the real structure of the problem. Because the atmosphere is not just dense. It is composed overwhelmingly of carbon dioxide. And that matters because carbon dioxide interacts with radiation in a very specific way. Sunlight comes in, the surface absorbs it, and then tries to release that energy as infrared radiation. But the atmosphere absorbs that outgoing energy and sends part of it back down, which heats the surface again, which leads to more radiation, which gets trapped again. And what you have is not a balance, but a loop, a feedback system that reinforces itself. The pressure makes the atmosphere thick. The composition makes it effective at trapping heat. And together they create a condition that doesn't drift toward equilibrium, but instead stabilizes at an extreme. And while all of this is happening, the air around you, the thing you would instinctively rely on, is not just unusable, it is fundamentally incompatible with your biology. It is heavy, suffocating, almost entirely carbon dioxide, with traces of other gases that don't help you in any meaningful way. And above you are clouds, but not clouds in the sense that you understand them. These are layers of sulfuric acid, suspended in a system that is chemically aggressive from top to bottom. And even the idea of rain, something that might suggest cleansing or cooling, is broken here, because droplets can form, but they evaporate before reaching the ground, turning the sky into an endless cycle that never completes. So if you step back and look at the whole picture, what makes Venus so lethal is not any single feature, but the way everything connects. The pressure is not just high, it enables the atmosphere to behave differently. The atmosphere is not just thick, it traps heat in a way that feeds back into itself. The heat is not just intense, it is permanent. The chemistry is not just hostile, it is sustained by the same system that creates the temperature and pressure in the first place. And once you see it that way, you realize something that is far more important than any individual detail. This is not a chaotic disaster. This is a stable outcome. Nothing here is going wrong. The planet is simply following the rules of physics, consistently, without compromise. And the result is a world where those rules, taken together, remove any realistic path for something like you to exist. The mistake didn't start with bad data. It started with a perfectly reasonable idea. If you take a planet that is almost the same size as Earth, with nearly the same mass, orbiting not dramatically farther or closer to the sun, and then you cover it completely in clouds so that no one can see what lies beneath, what would you expect? Not as a guess pulled from nowhere, but as a conclusion built from everything you already know. You would expect something familiar, because familiarity is the only tool you have when information is missing. And in the case of Venus, almost everything that mattered was hidden. So people did what you would have done. They looked at Venus through telescopes and saw a smooth, bright disk, consistently reflective, with no visible surface features at all. And instead of interpreting that as a warning, as a sign that something unusual might be happening, it was interpreted as continuity, as if the clouds behaved the same way clouds behave on Earth. Just thicker, more extensive, maybe more dramatic, but still part of a system that you already understood. Clouds mean water. Water means cycles. Cycles mean stability. And stability leaves room for something like life. The logic flows cleanly, step by step, and that's exactly why it's dangerous. Because a chain of reasoning can be perfectly consistent and still be built on the wrong assumptions. What nobody could see was that the clouds on Venus were not a thin veil over a familiar world. They were the entire story, a barrier that didn't just hide the surface but replaced the need to understand it. Beneath those clouds, there was no ocean, no weather system like Earth's, no cooling cycle waiting to be discovered. But without direct evidence, the imagination fills the gap, and it tends to fill it with what feels right rather than what is true. And this is where something subtle happens in the way you think. Because once an idea becomes comfortable, once it fits neatly with your expectations, it becomes harder to question, not because you're unwilling to question it, but because there is no obvious reason to do so. Venus became, in a sense, a mirror of Earth, not because it actually was one, but because it was easier to believe that it was. Easier to project what you already understood onto something you could not yet measure. But the problem with projection is that nature doesn't cooperate with it. When the first serious measurements began to come in radio observations, early probes, atmospheric data, they didn't gently adjust the picture. They broke it. The temperatures inferred were far higher than expected. Not slightly warmer, not just uncomfortable, but completely incompatible with the idea of liquid water on the surface. The atmospheric composition, once measured more directly, revealed overwhelming carbon dioxide, not the nitrogen-oxygen balance that supports life on Earth. And the pressure, once understood, was not a minor variation, but an entirely different regime. At that point, the comforting image of a humid, ocean-covered Venus couldn't survive, not because it was disproven in a single dramatic moment, but because every new piece of evidence made it harder to maintain. And this is the part that matters, not just for understanding Venus, but for understanding how knowledge actually changes. Because the shift wasn't emotional. It wasn't philosophical. It was forced by consistency. If the temperature is that high, water cannot exist as a liquid. If the atmosphere is that dense, the surface conditions must follow. If the clouds are made of sulfuric acid, then they are not part of a water cycle at all. So the image collapsed, and what replaced it was not just a different description of a planet, but a different realization. Two worlds can begin with similar sizes, similar compositions, similar positions in a solar system, and still diverge into completely different outcomes. Not because of randomness, but because of how small differences evolve over time under the same physical laws. And if you follow that idea carefully, without rushing past it, you begin to see why the original mistake was so natural, and why correcting it was so difficult. Because it requires you to stop treating Earth as the default model for every planet, and instead treat it as just one example among many. An example that happens to work for you, but is not guaranteed to repeat itself anywhere else. And Venus, hidden for so long behind its clouds, turns out to be the clearest demonstration of that. Forget the surface for a moment, because focusing on the ground is actually misleading on Venus. The real story is not where you stand, but what surrounds you. And if you strip everything down to its essentials, the entire character of this planet comes from a single thing taken to an extreme, the atmosphere. Now here's a question worth taking seriously. Not as a rhetorical trick, but as a way to build the idea properly. What happens if you take an atmosphere like Earth's and just keep adding more of it, layer after layer, without giving it a way to escape, not changing the rules, not introducing anything exotic, just continuing the same physics and letting it accumulate? At first, nothing dramatic happens. Just thicker air, slightly higher pressure, maybe a bit more heat retention. But if you don't stop, if you keep going, you cross a threshold where the system stops behaving like a gentle extension of Earth and becomes something else entirely. That's where Venus lives. By the time you reach the surface, the weight of the atmosphere above you has become so large that it produces a pressure about 90 times greater than what you experience on Earth. And that number matters only if you connect it to something physical, because it means every part of your body is being pressed on continuously with a force equivalent to being deep beneath an ocean. Except here the fluid is not water, but gas that has become dense enough to act like one. And the important part is not just the magnitude of the pressure, but its persistence, because there is no mechanism to relieve it. No fluctuation that gives you a break. Just a constant condition that defines the environment at every moment. But pressure alone doesn't explain the temperature. And if you try to treat them as separate facts, you miss the mechanism that ties them together. The atmosphere of Venus is composed mostly of carbon dioxide, and that choice of gas is not incidental, because carbon dioxide interacts with radiation in a very specific way. Sunlight arrives, passes through the upper layers, and reaches the surface, where it is absorbed and converted into heat. Under normal circumstances, that heat would be radiated back into space as infrared energy, and the planet would maintain a balance. But here the atmosphere intervenes. The carbon dioxide absorbs the outgoing infrared radiation and re-emits it in all directions, including back toward the surface, which means the energy that was trying to escape is redirected, partially trapped, and returned. The surface heats up further, emits more radiation, which is again absorbed and re-emitted. And what you get is not a static condition, but a feedback loop. Each cycle reinforces the next. And because the atmosphere is so thick, so massive, there is no easy pathway for the energy to escape efficiently. This is what people refer to as a greenhouse effect. But that phrase can be misleading if you think of it as something mild or controlled, because on Venus it doesn't stabilize at a comfortable level. It runs away. The system amplifies itself until it reaches a point where the surface temperature settles at an extreme around 475 degrees Celsius and remains there with very little variation. It is not that the planet occasionally becomes hot. It is that it has no mechanism left to become cool. And once you see that connection, the pressure enabling a massive atmosphere, the composition trapping radiation, the feedback loop locking in temperature, you realize that the atmosphere is not just a feature of Venus. It is the system that defines everything else. The heat is not an independent condition. It is a consequence. The pressure is not just a number. It is part of the mechanism. Even the chemistry of the clouds above depends on this same structure. So when you think about Venus as a place that crushes and burns, it's tempting to imagine two separate dangers, one mechanical and one thermal. But that separation is artificial. There is only one system operating consistently, following the same physical laws you already understand, just pushed into a regime where the results no longer resemble anything familiar. And that, more than any individual measurement, is what makes Venus so instructive, because it shows you what happens when ordinary physics is allowed to run without interruption, without moderation, until it builds a world that is stable, self-consistent, and completely hostile at the same time. Here's something that sounds simple, almost harmless, until you look at it closely. Venus has clouds. Now, if you hear that and your mind immediately fills in the usual picture, soft white layers drifting across the sky, part of a cycle that cools, rain, evaporates, and repeats, then you've just made the same mistake people made for decades, because the word cloud is doing more work than it should. It's smuggling in assumptions that don't belong here. And on Venus, nearly every familiar word turns out to be misleading if you don't take it apart. So let's take it apart. Those clouds are not made of water. They are made primarily of sulfuric acid, suspended in thick layers that stretch tens of kilometers above the surface, forming a global system that doesn't break, doesn't thin out into patches, doesn't give you glimpses of the world below, but instead wraps the entire planet in a continuous, reflective shell. And the moment you realize that, the idea of weather starts to shift, because weather, as you understand it, depends on balance, on cycles that move energy and material around in a way that eventually stabilizes. But here the system is not stabilizing anything. It is maintaining an extreme. Now think about what it means to have sulfuric acid floating above you, not as an isolated phenomenon, but as a persistent layer, constantly formed by chemical reactions in the upper atmosphere, where sunlight breaks apart molecules and allows new ones to recombine into something far more corrosive. These droplets gather, they grow, they move. And yes, if you want to use the word they, rain. But here's where the second illusion breaks, because that rain never reaches the ground. as the droplets fall, they enter hotter and hotter layers of the atmosphere. And long before they can touch the surface, they evaporate back into vapor, rising again to rejoin the cloud layers above, creating a cycle that looks like rain but never completes it. So what you have is not precipitation in the sense you're used to, but a kind of suspended process, an endless attempt at falling that is always interrupted, always reversed, a system that mimics a familiar pattern but never delivers its outcome. And if you follow that carefully, you start to see a deeper point. Even when Venus appears to behave like earth cloud, rain, atmosphere, it's only superficial. The underlying mechanisms are different, and those differences matter. Now let's go higher, because the atmosphere is not just chemically hostile. It is dynamically active in a way that is easy to miss if you're focused only on the surface. At the top of the cloud layers, winds move at incredible speeds, hundreds of kilometers per hour, circling the planet far faster than the planet itself rotates. This is something called superrotation, and it means the atmosphere is not just sitting there trapping heat. It is moving energy around in a system that is fast, efficient, and completely disconnected from anything like the gentle weather patterns, you know. And here's the strange part, down at the surface, where the pressure is highest, the winds are actually slow, almost deceptive in their calmness. But that doesn't make them safe, because when the air is that dense, even a slow movement carries significant force, like a heavy fluid sliding past you. Subtle but powerful. And once again, your instincts fail you if you rely on familiar cues. So now you have clouds that burn instead of nourish, rain that never arrives, winds that move faster than the planet beneath them, and all of it tied back into the same atmospheric system that traps heat and builds pressure, reinforcing everything else. And if you step back for a moment, you'll notice something important, something that keeps repeating. Venus doesn't just replace Earth-like conditions with more extreme versions. It replaces the entire logic of how those conditions behave. Clouds don't mean water. Rain doesn't mean cooling. Wind doesn't mean relief. Every concept is still there, but stripped of the meaning you're used to attaching to it. And that's what makes this part of the story so unsettling, because it forces you to confront a simple idea that's easy to ignore. The same words can describe completely different realities. And unless you understand the mechanism behind them, you can convince yourself that something is familiar when it absolutely is not. If you think Venus is strange because of its heat or its atmosphere, then you're still looking at the obvious parts, the things that announce themselves loudly. But some of the most important clues about this planet are quieter, buried in the way it moves, in what it has lost, and in what it no longer protects itself against. Start with something that seems almost trivial, the direction it spins. Every major planet in the solar system rotates in roughly the same direction, the same inherited motion from the cloud of material that formed them. And that consistency gives you a kind of expectation, a sense that rotation is just another detail you don't need to question. But Venus breaks that pattern. It rotates backwards, not slightly off, not tilted in a way that preserves the general rule, but fully reversed, as if something reached into its history and flipped it. Now, by itself, that doesn't kill you. You could stand on a planet that spins backwards and survive just fine. But it forces you to stop and ask a deeper question. What happened to this world that made it diverge so far from the norm? Because when a system breaks a pattern, it's rarely random. It usually carries the imprint of its past. And then there's the second detail. the one that sounds even more abstract until you really think about it, Venus rotates incredibly slowly. One full rotation takes longer than a full orbit around the Sun, which means a single day on Venus is longer than its year. But even that statement hides something more subtle, because when you combine the slow rotation with its backward spin, the actual cycle of sunlight across the surface becomes a strange, stretched out rhythm, nothing like the regular day-night alternation you're used to. Now ask yourself what that does to a planet. On Earth, rotation helps distribute energy, smoothing out temperature differences, driving weather systems, maintaining a kind of dynamic balance. On Venus, that familiar rhythm is distorted, and although the thick atmosphere dominates the climate, the slow, reversed rotation is part of the story of how this world evolved into something so different. But the real turning point in understanding Venus is not how it spins, it's what it lost. Because all the evidence we have suggests that Venus may once have had water, not just traces of it, but enough to form ocean, or at least significant bodies of liquid on its surface. And that possibility changes everything, because it means Venus did not start as the world we see today. It started closer to something you would recognize. So what happened? Here's where the pieces come together. And you have to follow the chain carefully. As the sun's energy heated the planet, more water evaporated into the atmosphere. And water vapor, like carbon dioxide, is a greenhouse gas. More vapor meant more heat trapped. More heat meant more evaporation. And the system began to amplify itself. Eventually, the temperature rose high enough that the oceans, if they existed, would have boiled away entirely, turning the planet into a world wrapped in steam. But that's only the beginning. Once water is in the upper atmosphere, it becomes vulnerable. Ultraviolet radiation from the sun can break water molecules apart into hydrogen and oxygen. And hydrogen, being light, escapes into space. Over time, this process strips the planet of its water, molecule by molecule, until what was once abundant becomes almost completely absent. The oxygen that remains can react with the surface or other atmospheric components, leaving behind a world that has lost one of the key ingredients for life. And here's where the absence becomes just as important as the presence. Because Venus does not have a strong global magnetic field. On Earth, the magnetic field acts like a shield, deflecting charged particles from the solar wind, protecting the atmosphere from being eroded too quickly. Venus lacks that protection. So while hydrogen escapes easily, other particles and interactions continue to shape the atmosphere without resistance, contributing to the long-term transformation of the planet. Now step back and look at the pattern again. A planet that spins the wrong way, rotates too slowly, loses its water through a runaway process, and lacks the magnetic protection that might have slowed that loss. None of these factors alone fully explain Venus, but together they tell a story, not of sudden catastrophe, but of gradual, irreversible change. And this is the part that matters. Because Venus is not just a strange world frozen in an extreme state. It is the result of a sequence, a progression where each step makes the next one more likely. Until the planet crosses a threshold it cannot return from. And once that happens, the direction of time, at least for that world, becomes very clear, not toward recovery, not toward balance, but toward a stable condition that is entirely incompatible with the kind of environment you would need to survive. There's a quiet assumption people make once they understand how extreme Venus is. And it sounds reasonable at first. If a planet looks this hostile, this stable in its brutality, then whatever created it must be in the past, something that happened long ago and left behind a kind of planetary ruin, like a fire that has already burned through everything it could consume. But Venus doesn't fit that picture, because when you start looking carefully at its surface, not through imagination this time, but through radar mapping and thermal data, you begin to notice something that shouldn't be there if the planet were truly finished, and that is change. Not rapid, obvious change like shifting continents you can watch in real time, but subtle evidence that the surface has been resurfaced, covered, renewed on a scale that suggests something much more active beneath it. The number alone is enough to make you pause. Venus is covered with thousands of volcanoes, more than any other planet in the solar system, and not just small. Isolated features, but vast volcanic plains, enormous lava flows that stretch across hundreds or even thousands of kilometers, structures so large that they redefine what you think of as a volcanic landscape. And the strange thing is, the surface doesn't show the kind of gradual aging you might expect. There are relatively few impact craters, and they are distributed in a way that suggests the surface was, at some point, almost entirely renewed. Now think about what that implies. If a planet's surface is relatively young in geological terms, then something must have been active enough to erase the older record, to cover it, to replace it. And on Venus, the most plausible explanation is widespread volcanic activity. Not isolated eruptions, but events large enough to reshape the entire surface over time. And here's where it becomes more than just a geological curiosity, because volcanoes don't just change the landscape, they change the atmosphere. Every eruption releases gases, carbon dioxide, sulfur dioxide, and others directly into the surrounding environment. And on a planet like Venus, where the atmosphere already traps heat so effectively, those additions don't dissipate easily. They accumulate, reinforcing the same greenhouse system that keeps the planet hot. So now you have a feedback loop that extends deeper than before, not just in the atmosphere, but connecting the interior of the planet to the sky above it. The heat inside the planet drives volcanic activity. The volcanoes release gases. The gases thicken and maintain the atmosphere. The atmosphere traps heat, and the trapped heat ensures that the system remains active. It's not just a surface phenomenon. It's a planetary scale cycle. And this leads to a question that's much harder to answer than it first appears. Is Venus still active today? For a long time, we didn't know. The evidence was indirect, based on surface features and crater counts, suggesting that major resurfacing events happened in the past, but not necessarily telling us what is happening now. But more recent observations have started to change that picture. Variations in thermal emission, changes detected in specific regions, hints of sulfur dioxide fluctuations in the atmosphere, all of these point toward the possibility that Venus is not a dead world, but one that is still geologically alive, still releasing energy, still reshaping itself. And if that's true, then Venus is not just the result of a runaway greenhouse effect that happened once and stabilized. It is a system that continues to sustain itself through internal processes. A planet that never fully cooled, never settled into inactivity, but instead remains in a state where its interior and its atmosphere are linked in a continuous exchange. Now compare that, just for a moment, to how you might think about a planet like Earth, where geological activity also exists, but is part of a broader balance that includes oceans, plate tectonics, and a climate system that, at least for now, regulates itself within a range that supports life Venus shows you what happens when that balance is absent. When geological activity feeds directly into atmospheric extremes without any mechanism to counter it. So the picture shifts again. Venus is not just hot, not just dense, not just chemically hostile. It is active continuously, persistently, driven by processes that don't stop just because the surface has become uninhabitable. And that changes the way you should think about it, because it means this is not a snapshot of a past disaster. It is an ongoing state, a world that continues to evolve, not towards something more stable or more life-friendly, but toward maintaining the conditions that already make it so extreme. And once you see that, it becomes harder to think of Venus as a place that simply ended up wrong, and easier to see it as a system that is still working, still producing outcome, just not the kind that you would ever want to be part of. There's a difference between understanding something in theory and actually touching it. And Venus is one of those places where that difference becomes almost brutal, because for a long time, everything we knew about it came from inference, from equations, from indirect measurements that told us what should be happening. But there's always a gap between knowing and proving. And sooner or later, someone decides to close that gap. So we sent machines, not once, not cautiously, but repeatedly, knowing in advance that most of them would fail. Because if you take everything we've just built, the pressure, the heat, the chemistry, and you ask a simple question, can a machine survive here? The honest answer is not encouraging. And yet, step by step, mission after mission, the Soviet Venera program pushed further than anyone else. Not because the environment became easier, but because the engineering became more determined. The early attempts didn't make it. Some probes were crushed before they could transmit anything meaningful. Others failed in the descent, overwhelmed by conditions that were still not fully understood at the time. And this is where it becomes interesting again, because failure here wasn't just failure. It was data. Every broken signal, every lost transmission narrowing the uncertainty, telling you not just that Venus is hostile, but how it is hostile. Then came Venera 7. It didn't land the way it was supposed to. It fell, damaged, partially compromised, and for a moment, it looked like just another failure. But then it started transmitting faintly, inconsistently, for about 23 minutes. And in those minutes, something changed. Because for the first time, we had direct data from the surface of Venus, not speculation, not inference, but measurement, confirming what had been predicted: the temperature, the pressure, the reality of the environment. And that's an important detail to hold on to, because it shows you something about science that often gets overlooked. It doesn't require perfection to move forward. It requires persistence. And sometimes a broken machine is enough. Later missions improved on that. Venera 9 and 10 sent back the first images from the surface. Grainy, distorted, but unmistakable, showing a landscape of fractured rock under that dense orange sky. Venera 13 went further, capturing color images and surviving for over 2 hours, long enough to analyze the composition of the soil, long enough to prove that even in a place like this, careful design can extend the boundary of what's possible. And yet, even in those successes, there's something almost tragic, because every one of those machines was built with a limit, a known endpoint. They were not designed to explore indefinitely, not to move, not to adapt, but to endure for as long as possible before the environment inevitably won. cooling systems, pressure-resistant shells, insulation, all of it, buying time, not survival. There's even a moment that feels almost like a quiet joke from nature itself. Venera 14 carried an instrument to analyze the soil, but when it tried to make contact, it ended up testing the cap that had been ejected during landing instead of the ground beneath it. Even in a place as extreme as Venus, small details still matter. And mistakes don't disappear just because the environment is unforgiving. Now step back from the machines for a moment and look at what they represent. Because this isn't just a story about engineering reaching its limits. It's a story about curiosity, refusing to stop at theory, about the need to confirm, to see, to measure directly, even when the cost is almost guaranteed failure. And that brings us to the part that matters beyond Venus itself. Because everything you've seen, the runaway greenhouse effect, the loss of water, the thickening atmosphere, the feedback loops that reinforce themselves, none of it violates the laws of physics, we understand. There is nothing exotic here, nothing that requires a new theory to explain it. It is all built from the same principles that operate on Earth, the same interactions between radiation, gases, and energy balance. The difference is scale and direction. Venus shows you what happens when those processes are allowed to run without interruption, without a stabilizing mechanism, until they lock a planet into a state that is self-sustaining and extreme. It is not a prediction of Earth's future in a simple sense, not a direct path we are inevitably following, but it is a demonstration of what is possible within the same framework of physics. And that's the warning. Not that Earth will become Venus tomorrow, but that the systems we rely on, the atmosphere, the climate, the balance between incoming and outgoing energy are not guaranteed to remain stable just because they are stable now. They are processes, and processes can change. So when you look at Venus, you're not just looking at another planet. You're looking at a case study, a full-scale experiment already completed, showing you one of the ways the world can evolve when certain thresholds are crossed. And once you understand that, the question is no longer just what is Venus like, but something much harder to ignore. How close can a planet get to that kind of transformation before it realizes what's happening?